let me define what are the generating series. So we can associate several series with species, and we want to look at these series in detail. Okay, so first we are going to define what is the exponential generating function of the species f. So what is that? So given a species f, we mentioned that the cardinality of f of u for any finite set u only depends on the cardinality of u, right? So therefore, I can just talk about a fixed set 1, 2, 3, etc. n as an n element set. So if I am talking about all the n element sets, then the cardinality of f of u for any n element set u is actually equal to the cardinality of f of set 1 to n, right? Because that is also another n element set. And this cardinality, right, the number of structures of type f on an n element set is denoted by fn, small fn. Now, as we know, to form generating series, right, we can basically multiply by x raised to n, and then depending on how fn grows, we will either normalize by n factorial or something like that. So here we are going to do that. So we define f of x as summation overall n greater than 0 fn x raised to n by n factorial. And this, as we have seen in the case of generating functions, is called the exponential generating function of the species f. Okay, so this basically counts fn, and then if you want to recover fn, you have to just find out the coefficient of x raised to n by n factorial in f of x. Now, what is that? This is basically using Taylor series expansion. Whenever you are given the function f of x, you can use Taylor series expansion and then find out by multiply by n factorial, right? Look at the coefficient of x raised to n in f of x, and that is basically what is that by Taylor series. It is d raised to n f of x by dx raised to n evaluated at x equal to 0, right? So therefore, or if you want, you can say Maclaurin series. Doesn't matter. So expansion at evaluate at x equal to 0, and that is going to give you f of n, fn. Now, a formal power series in any number of variables is expressed, right? So you can talk about formal power series in one variable, two variables, or infinitely many variables. So if you have infinitely many variables, you can just define it as follows, right? X of, let's say, x1, x2, etc., right, is summation overall tuples n1, n2, n3, etc., right? X n1, n2, n3, etc., then x1 raised to n1, x2 raised to n2, etc., whatever was that same tuple, right? N1, n2, n3, etc., divided by c n1, n2, etc., the same tuple of elements, where this c n1, n2 is a given family of non-zero scalars, right? In our case, it was n factorial here. It could be anything else here, right? So that kind of thing is basically a formal power series, and you can generalize it to any number of variables as you please. Now, here are some examples of species again. So S is the species of permutations, and what is S of x? The generating function S of x is 1 by 1 minus x. Why? Because we know that the number of permutations, right, on an n element set is basically n factorial. So because it is we have n factorial of them, summation n factorial by n factorial is going to be summation 1, which is the series 1 by 1 minus x. Then if you talk about the species of linear orders, right? So we know that there is also n factorial many linear orders. So L of x is also 1 by 1 minus x, where L of x is the exponential generating function for the species of linear orders. C of x is the cycle species, right? Cyclic permutations. Then what is that? It is basically summation. We know that there is n minus 1 factorial of them. So therefore you will get minus log of 1 minus x. which follows from this summation, right? N minus n factorial by n factorial into x raised to n. Similarly, can you find out the the exponential generating function for the species E of sets, the species epsilon of elements, species P of power sets, and species X of singletons, and species G of graphs, simple graphs. So take it as an exercise and try to find out what are the generating functions or generating series. Now, so we are talking about so far the counting the objects of a particular species that you can make on a set U with, let's say, n elements, right? Now there could be several objects, when I use the set, the set relabeling, right? There could be several of them, may be isomorphic. So there will be several isomorphic structures. When I talk about graphs on the set 1, 2, 3, 4, you will have several graphs, but several of them could be isomorphic. Now I don't want to, let's say, that count all the all these isomorphic things separately. I want to just find out how many different inequivalent structures are there, right? So for that, I can consider the isomorphism class, right? Isomorphism types of F structures, species F structures on the set, let's say f of n, right? So take any n element set, 1 to n, let's say here. Look at f of n, and then we can look at the isomorphism types of this, this type on f of n, right, on this set. Now let me define an equivalence relation as follows, right? So what is the equivalence relation tilde? It says that for any two structures S and T in f of n, right, S is the equivalent to T if and only if I can find a bijection from the set 1 to n to itself, such that f of pi, the transport of pi, right, takes S to T, right? The structure of type S, structure S of type F to structure T of type, right? So if that is true, so if you can find such a bijection pi, then we say that S and T are basically equivalent, that they are isomorphic. That is the idea. Okay? Now, an isomorphism type of F structures of a fixed order, let's say n element set, is an equivalence class of the equivalence relation tilde on f of n. So the equivalence classes are called isomorphism types. Okay. So it basically f of n mod tilde, right? So the equivalence classes. So let me denote this by T of f of n. Then T of f, right? For this is for an n element set you are doing this, right? So for all possible structures, we have T of f now, summation overall n, right? T of f, right? So n greater than 0, you take f0, f1, f2, etc., right? Which are structures of type f on an n element set, and then you are looking at the equivalence classes of these structures. Now let me denote by small fn tilde as the number of isomorphism types of f, right? How many distinct type of structures are there? Then the isomorphism class generating series, which is called f tilde of n, is the ordinary power series. F tilde of n is equal to f tilde of x. Sorry, f tilde of x is equal to summation overall n fn bar of fn bar times x raised to n. This is the ordinary power series, not the exponential power series. Because when you are talking about isomorphism types, right? We are just counting the class, how many classes are there. Usually the numbers grow much smaller, right? So therefore we don't want to use exponential generating series. So then we have the ordinary power series. And Fn tilde is now is basically the cardinality of T of Fn, right? So T of Fn was Fn of n, right, on the set 1 to n, modulo the equivalence relation. So examples, right? So for example, L tilde of x, right? You're looking at linear orders. L tilde of x is 1 by 1 minus x, because when we are arranging objects, right, you have n factorial many ways to do that. But if you consider all of them to be identical, right, the labeling is not important, then whichever order that you are going to put in a line, it is exactly the same line. So there is only one way to do that. And because of this, summation, x raised to n and reduces to 1 by 1 minus x. So therefore, we get that the isomorphism type generating function for the linear orders is 1 by 1 minus x. Right? Now, if you look at the cycle permutations, right? C tilde of x. Now, what is C tilde of x? Can you show that it is actually equal to x by 1 minus x? Right? So it basically is is a shift by 1 for L tilde of x. And can you connect this and see why this is this? Similarly, if you look at E tilde of x, right? E is the species of sets. So what is E tilde of x? So I am putting a set structure on you. So it does not matter. Then there is only one. So therefore it does not matter whether it's labeled or not, right? So you will still get a set with just one unknown. The count is going to be exactly 1. So it will also be 1 by 1 minus x. What is the species of elements? Again, can you show that it is actually x by 1 minus x? If P is the species of power set, what is P tilde of x? Okay, show that it is actually 1 by 1 minus x whole square. Now, even more interesting is that, S tilde of x, right? What was S? S is the species of permutation. And we can show that S tilde of x is equal to product k is equal to 1 to infinity, 1 by 1 minus x raised to k. Now, what you can see from this is that S tilde was this function. On the other hand, L tilde was just 1 by 1 minus x. Now, when we are looking at linear orders and permutation, right, we often have this tendency to see them as kind of the same thing, right? We are permuting objects, and we are arranging them in n factorial different ways. Since there is a bijection between these two, we think that they are kind of the same thing, right? Often there is a mistake, feeling that linear orders are and the same as permutation. On the other hand, this tells you that when we look at the unlabeled structures, right, the isomorphism classes, we see that they are indeed different objects, because S tilde of x is actually very different from L tilde of x. Then for singletons, x tilde of x again is equal to x. These things you can try to derive these identities as a homework. Now, some remarks. So this is something that I already remarked, that S of x is equal to L of x equal to 1 by 1 minus x. But S tilde of x is different from L tilde of x. Thus, permutations are actually different from linear orders. Now, let us look at the cycle index series. Okay. So So maybe I should just mention one more thing, right? See, S of x and L of x was 1 by 1 minus x, right? But see, if you look at L of x, L of x was 1 by 1 minus x, and L bar of x was L tilde of x was also 1 by 1 minus x. Right? This should not confuse you, right? Because you know, here L of x is 1 by 1 minus x because it was the exponential generating function, and we were actually dividing by n factorial. On the other hand, here we have the ordinary generating function where we are not dividing by n factorial, therefore the count is 1, right? And there it was n factorial, we made it 1 by dividing by n factorial. So these two are indeed very different, right? L of x and L bar of x. One is exponential generating function, which is 1 by 1 minus x by chance, and L tilde of x is also 1 by 1 minus x, but it is the ordinary generating function. Now, because these are different, we see that permutations are different from linear orders or species. Now, finally, I want to introduce one more series associated with with the species, which is called cycle index series. Okay. So, to define that, let us first define and look at the following. So, U is a finite set, and sigma is a permutation of U. Okay. Where sigma, the permutation has the cycle type. So we studied this, in our class earlier. Cycle type, sigma 1, sigma 2, sigma 3, etc. Where sigma k in general is the number of k cycles in sigma, right? So sigma k counts the number of k cycles in sigma. Now, if you are given an n element set, right, U, then we will see that this the cycle type, right, will all be 0 after the nth time, right? Sigma n n plus 1 onwards will all be 0. This is something immediately clear. There cannot be a cycles of larger length. Now, we denote by small fix of sigma as the cardinality of fix of sigma, where fix of sigma, as we saw earlier again, right, was the number of elements fixed by the permutation sigma, right, which is actually equal to sigma 1, right? It's basically the number of unit cycles, right? Single cycles in the permutation, the representation of permutation as cycles. Now, the cycle index series of a species F of structures is the formal power series in an infinite number of variables, of course. Set F of x1, x2, x3, etc. is equal to summation overall n greater than or equal to 0, 1 by n factorial. You should be able to see where this is coming from, right? Summation overall sigma belong to Sn, fix of f of sigma, x1 raised to sigma 1, x2 raised to sigma 2, etc. Right? So this is something it should be pretty clear where these objects are coming from, what these objects mean from our short excursion we did to Fourier's theory, right? So we don't go into the details further. Think about this and try to understand. If you have any questions, come back to me. Now, here is some examples I am going to give. I am not going to go into details how I obtained this or how we obtained this. It takes a lot of time to explain many of these things, but you should be able to work out the details for at least some of these examples. Okay. So as a homework, you can try to figure out why they are the same. So if you look at the cycle index series of the linear structures, right, linear orders, the ZL of x1, x2, etc. is 1 by 1 minus x1. Okay. Now, on the other hand, if you look at the cycle index series of the species of permutations, that is actually 1 by 1 minus x1 into 1 minus x2 into etc. It goes on. What is the cycle index series of the species E of sets? It is E to the power x1 plus x2 by 2 plus x3 by 3 plus etc. Okay. Try to see why this is the case. Okay, so it should be pretty clear once you understand what is this exponent's meaning, okay, and how you connect it with the cycle types that we are talking about earlier, sigma 1, sigma 2, etc. And if you do that, you should be able to figure out why this indeed makes sense. Then, as Homer derived the cycle index for the species epsilon of elements. Second question is to prove that f of x is equal to, right? So f of x was the exponential generating function for the species f, and this you can obtain directly from the cycle index by substituting ZF with where the first index has x and everything is 0. So x1 goes to x, right? x2 is x3, etc. is 0. So if you substitute this in ZF, you should get f of x, right? Let's look at one example, right? Here, if you substitute for, this is just x, so I will get 1 by 1 minus x, and that is precisely the what is called precisely the exponential generating function for the linear orders, right? Then f tilde of x also you can obtain from the cycle index. So cycle index contains much more information than what is contained in the exponential generating function and the type generating function, because you can get both of these directly by just simple substitutions. For example, f tilde of x is ZF of x square, x cube, etc. So you just replace xi with x raised to I, right? And in ZF, and you will get f tilde of x. So the type generating function can be computed. In fact, to compute the type generating function for most of the species, you need to go through finding the ZF and then do this. It's not immediately clear how to count the type generating function without using the help of the cycle index. I mean, for some things like linear orders and all, we know immediately, but otherwise it is not very direct. So prove these two statements, okay? And these are not very difficult. Just substituting this, and you will see what is happening there, and using some of the observations that we have before, you should be able to do this. Now let me define operations on species. So what do I mean by operations on species? So I am talking about addition, or some products, taking derivatives or exponentiations, compositions, and all kind of things we can talk about. So what is the meaning of sum of two species? So given species f and g, right? F plus g of u, right? So see, this is the basic way to define any object on a species. Given any finite set u, the species tells you the rule to generate fg. I mean, whatever the species of u for any finite set, right? So therefore, f plus g of u should tell you how to do that. And what is this? I define this as the disjoint union f of u plus g of u. Okay, so f plus g of u is f of u plus g of u, where I consider the disjoint union in the sense that it is possible that the species f and g are such that for some elements, for example, on the empty set or something else, it might create the same kind of objects. But I want to distinguish them by marking it as the elements coming from the species f and the elements coming from g, right? So I want to make sure that the union is disjoint. So I can do this by specially marking each type f structure with with a marker that it is coming from f, and each g type structure with another marker to say that it is coming from g. So this way I can make the disjoint union. And what is the disjoint union looking like? It is basically right? So f plus g on this structure is in the pictorial manner. It is basically an f structure on the same set plus a g structure on the same set, right? So all possible f structures here you can make, and all possible g structures you can make on the same set, and all of them put together is basically the f plus g structures on the set we are looking at. And if Cn is the number of structures on an element set of type f plus g, and An and Bn are the corresponding number of type f elements and g elements on the same set, then Cn must be equal to An plus Bn, because if we are doing this, this should be the case, right? So what we want is that Cn is actually equal to An plus Bn, and for every function, every bijection from U to V, we should have the transport again a bijection which takes f plus g of U to f plus g of V, right? This should be again intuitively clear. So we want this also, and we also want the functions, right, to be adding, right? The generating function should be added. The exponential generating functions should be added together. So an example is the species of sets. E is the species of sets. Then what is the generating function for E, which is e raised to x? Okay, we saw this, or you can prove this. Now we know that e raised to x actually equal to cos h of x plus sin h of x, right? Something that we have studied, and in calculus. But what is even more interesting is that now the species E can be written as the sum of two species, right? Which is the set of all even sets and set of all odd sets, right? So the species of even sets and species of odd sets. Now, what is the generating function for the species of even sets? That is actually cos h of x, and the generating function for the species of odd sets is sin h of x. So since E is equal to, right, so any set is basically either an even set or an odd set, and the generating function for even set is this, and generating function for odd set is this, we should have this identity, right? E raised to x must be equal to cos h of x plus sin h of x. So if you find it easier to prove that E is this and O is this, then you have another proof of this identity, or using this identity you have a proof of this. I mean, all these things one can do. Now, a family, Fi of species is said to be summable family if for any finite set U, okay, Fi of U, right? The Fi type, right, of objects on U is empty except for a finite number of indices in I, right? So if there are infinitely many, so the I could be an infinite family, right? But if only for finitely many such i's, Fi can be defined, right? For everything else, it is basically empty. Then we say the family is summable, because when we sum over all these things, we want to still remain in the domain of finite numbers, right? We are always talking about finite sets, and the finite set of objects, and finite set of objects that you can make out of this finite set of objects. So therefore, we want to always stay in the finite domain. So we will say that, okay, a family is summable, right? If in that family, right, indexed by I, only finitely many i's define any objects, and everything else produces empties. Then we have that summation overall I Fi of U is basically the union of Fi of U cross I. So this Fi of U cross I, the cross I is basically used to make sure that we are looking at disjoint union. Okay, that is the only purpose of that. And whenever this is empty, we don't have anything here in the product. And this also satisfies that if whenever there is a bijection sigma, right? So some summation fi of sigma, the transport of the summation of s comma I is basically the structure uh, in I is defined by the transport fi of sigma of s comma I, where I is just the index marker, right? Just to differentiate the objects coming from fi. Now, this is the general setting, and for the special case, we have this canonical decomposition when we want to separate the elements that we are making, right? The structures that we are making on sets of different cardinality. So, when you are looking at the set U and you are looking at the n element set U, and so what we want to say is that like Fn is basically going to look at the type F structures that you make on n element sets only, right? So Fn of U is basically F of U if U has n elements precisely, and if U has more or less elements, there is nothing that you can define on that belongs to Fn, right? So this way we can always decompose. So the family F is now, right, the species F is the sum of the species F0, F1, F2, etc. Where Fi is the species made out of an I element set, right? The species or the structures of type F made out of I element sets. So only I element sets can produce elements in Fi. So because of this, we know that there is only finitely many indices, and therefore it directly follows from the above property that we have the summability, and therefore I can write it as the disjoint union of f0 plus f1 plus etc. So example is you're looking at polygons. So polygon with 0 elements, 1 element, 2 elements, 3 elements, etc. And then all of them together forms the species of all polygons. Now we quickly look at the product of two species. So f and g are species. I denote by f dot g the product species fg. So what is the product species fg? Its generating function fg of x is the product of the generating function. So we want this, and we are going to define the product as something that works out for this property to hold. Okay. So what is Cn? Cn is the number of elements of type f dot g on an n element set. Okay. And that is precisely equal to summation k equal to 0 to n choose k, a k, bn minus k. So this all we saw when we define the product of exponential generating functions, right? And what is this? So the product of two species is denoted in pictorial way as follows. You have this set, right? And you are putting an f dot g structure on this, which is equivalent to taking the same set, right? Finding some subset, putting an f structure on this subset, looking at the complement, right? Or the of this, and putting a g structure on the remaining elements, right? So this picture tells much more things that one can express in words. How the product species looks like is very clear from the picture, right? So basically, when we are looking at the product, it's basically partitioning the set U to two sets U1 and U2, right? Put an F structure on U1 and a G structure on U2, right? And then because of this, we know that what happens to F dot G on U is basically the different ways you can do this to U1 and U2, right? F of U1 and F of U2, you are looking at the Cartesian product. And this will be our structures, right? The structures will be of this type, f of u1 cross g of u2. And sum over all these u1, u2, right, which are basically partitions of u2, two sets. And that should give you the species f dot g, right? And what happens to a permutation sigma or a bijection sigma? The bijection sigma is taken, right, by f dot g, right, the product, a sigma, the transport of sigma under this product is basically what happens to an element S, right, an object of type f dot g. Now, what is S? S is a product, is an object of type f of g. But we know that any such S is basically of this type, right? F of u1 cross g of u2. So therefore, it has actually two components, right? So let us say that that is basically f and g, right? So small f and small g. So if S is small s is f comma g, then this sigma must act as separately on f and g, where sigma I is the projection of sigma, right? The restriction of sigma to just ui, right? So sigma I acts on the entire u1 cross u2, but the restriction of sigma to u1 or u2 will give you sigma 1 and sigma 2. So f dot g of this sigma is basically f of sigma 1, right? So what happens to sigma 1 under f, right? The transport of sigma 1 in f and of f, right? F is basically a structure in f of u1. And similarly, g of sigma 2 of g, where g is a structure of g of u2, and g of sigma 2 is the transport of sigma 2 with respect to g. So this is something that will be satisfied. That should be satisfied. So let's look at a very interesting example. Okay. So we look at the example of permutation, right? So permutations are the species of permutations denoted by S, and we know that permutations are basically cycles, right? Basically cycles. So so you have several cycles here, right? And these cycles define the permutations. Now we observe that, like in this permutation we have these cycles with more than one element, right? And there could be some cycles with just one element. So you collect all the cycles with one element, put them together. Since the one cycle does nothing, right? It maps to itself. These are basically elements which does nothing else, right? So I collect them together, it forms a set, right? So I form a set, partition u1, right? And then you have the cycles where you have at least two elements, right? Now, where all the cycles have two elements, the product of such cycles will be a permutation where no element is fixed. So therefore, they are called the derangement, right? Derangement is a permutation without any fixed points. So therefore, we see that we can see any permutation as basically a possibly empty set of elements together with derangements, right? So we see that the species of permutations is basically the product of the species E of sets and the species der of derangements, right? Because given any permutations, I can do this, right? I can basically look at the one cycles, form a set out of all these elements, and then the remaining larger cycles defines a derangement. And on the other hand, given any set and any derangement, right, like of the remaining elements, I can put them together, and it defines a permutation, right, of all the elements. So therefore, there is one-to-one correspondence, and then we see that the species of permutations is the product of species of sets and derangements. Now, this helps us to compute, for example, the generating functions for derangements. If we know what is the generating function for S and D, right? So we computed this earlier. So S is equal to E dot der, and therefore derangement is equal to S divided by E, right? What is S divided by E? S of x by E of x. What is S of x by E of x? S of x is E raised to minus x. No, S of x is 1 by 1 minus x. And E of x is E raised to x. So therefore, I get E raised to minus x by 1 minus x. Now what is e raised to minus x? If you expand it, it is summation minus 1 raised to I, x raised to I by a factorial, where I greater than equal 0, and summation x raised to j, where j greater than equal 0, for 1 by 1 minus x. Right? This is the geometric series. Now the product of these two, right, we can immediately find, because the coefficients here are just ones, right? So therefore, what is the product of these two? And you are looking at the coefficient of x raised to n by n factorial. That is basically n factorial into, look at the terms which are going to contribute to x raised to n, right? I have to take some element from here, and the remaining numbers should come from here, so that j plus I must be equal to n, right? So if I collect them all together, I know that there could be at most n plus 1 times. So 1 minus 1 by 1 factorial plus 1 by 2 factorial minus etc. Minus 1 raised to n by n factorial. So this you will get from here, and therefore dn is basically this, right? N factorial into 1 minus 1 by 1 minus 1 by 1 factorial plus 1 by 2 factorial etc. And this is the formula for dn we calculated earlier using principle of inclusion and exclusion. But now here we, without using any such thing, we can directly compute the formula just by looking at the generated function for the permutations and sets. So this is a nice way to compute other generated functions which are not easy to combine. Another example is the power set of all power sets on set U is basically the product of E with itself, right? So E is the species of sets, so species of sets with itself. And why is this? This should be clear, because any subset is basically partitioning set U to U1 and U2, right? One is to keep and the other one is to throw out, right? That forms a subset. So basically power set of X is basically the product of E with itself. And that should also make sense, because we get e raised to 2x, right? The number of objects of this type is basically if you look at the coefficient of x raised to n, it will be 2 raised to n, right? On the other hand, when it is e raised to x, it is just one. There is only one set structure on it. So you will get this directly from here. Okay, so with that example, I will stop for today. Then we will continue with more examples. More examples of more operations on species. And with that, let me stop today.